Hi, this is video 3 in the series of the AP Physics C Mechanics Calculus Basic Skills Guide. And in today's video, we're going to be going over how to derive the position function given an initial condition and your velocity function. So the question is asking us, a particle's velocity can be described as v of t corresponding to 2t plus 6. And the question wants us to derive an expression for the particle's position as a function x of t given the particle's initial position x of 0 equals 0. So we know that this refers to x of t, which is the function we want to solve for, right? And we know that at x equals 0, your t corresponds to 0. And we want to solve for the entire velocity function, right? And in a previous video, we went over the relationship between your position and your velocity function. So what do these have in common that we went over in our previous videos? Well, we said that dx dt, or the instantaneous slope of your position function, gets you your velocity function, right? These two match with each other, right? So for example, if I were to draw like the position function, oftentimes we would have something like this. In physics 1, you would see that you have your x as a function of time, and then you can figure out your position, you can figure out your velocity by taking the average rate of change of your position over certain intervals. So for example, from here to here, your velocity would be 0. But from here to here, your velocity would be negative. And what you can do, in fact, is you can extrapolate that into going in the opposite direction, where you have your velocity. And you can figure out your total displacement, right? And what we can do is we can just add up all these areas as like simple geometric shapes. In this case, it would just be a triangle and a rectangle. So you can just do base times height all over 2. And that would describe the total area, or the total displacement. And in calculus, what you can do is you can use something called an integral to get back your original function, because if you add up all the area like we did in the velocity, you get back the total displacement of your position. And in fact, what we can do in this case is that we know our v of t is equal to 2t plus 6. We want to get back to x of t, and we already know that x of 0 equals 0, so we know that when t equals 0, x equals 0. And this is going to be an equation on your equation sheet that we will have down, so it's not necessarily important to memorize, but it's just good to know that when v of t, like we said in our previous videos, is equal to dx dt, we can say that v of t dt, you can think of this as a fraction essentially. V of t dt equals dx. You can integrate this to get your position function. Because like we said earlier, you take the derivative, you take the slope of x of t, you will get back v of t, right? And it goes in the opposite direction too. If you take the integral of your velocity function, you will get back your position function. So in this case, we know that our velocity function will be 2t plus 6 dt equals integral of 0 to x of t dx. And then we know it's going to be from 0 to t, because we know that our initial condition for our bounds is going to be from 0, like I said in the problem, x of 0 is equal to 0, to t, because it's a function of t, right? Because it's going to go on and on, because we don't know, it didn't say like when the t is going to stop or when it's going to end. So we're going to use the variable t to describe it. And x of t on the right side here just refers to our position function that we're going to be solving for, right? And in this case, what we will be using is this property called the reverse power rule, where if you are integrating some function x to the n dx, what you'll get back in return is x to the n plus 1 all over n plus 1. And To make sure that this is true, we take the derivative of this right here with respect to x, and we use power rule to apply it, right? So it would be n plus 1 times x to the n plus 1 minus 1 all over n plus 1. This and this cancel. This goes, and it just goes back to x to the n, right? So that's the property that we'll be using to solve for this. And this is another equation that's on your equation sheet, so you don't have to worry about memorizing it as well. It'll be with all the other calculus equations, right? And we can use this property to solve now for this. And after we solve for our antiderivative, our integral, you have to plug in your bounds now to solve for the new function, right? So in this case, we have 2t. We have to do the antiderivative of that. It's going to be 2t, 1 plus 1, all over 1 plus 1, plus 6t to the 0 plus 1, because it's a constant, right? All over 0 plus 1. So then we're going to get 2 over 2t squared plus 6t, evaluated from 0 to t. And then we have x on the other side, evaluated from 0 to x of t. And in this case, we have 2 over 2, this just goes to 1. So we're going to get t squared plus 6t from 0 to t. We can actually move up here instead to solve this part. So we get t squared plus 6t evaluated from 0 to t, which becomes t squared plus 6t minus 0 plus 0, because when you plug in 0 into both of these, it just gets you 0. And you do x of t minus 0, because when you plug in 0 for x, you get back x. So then in this case, our position function gets back t squared plus 6t equals x of t. And in fact, if we want to double check our answer, we can take the derivative of the position function to get back our velocity function. So we take the derivative of 2t, which using power rule, we would get 2t. And then we get plus 6 here equals v of t. And then through this derivation, you would see how you can solve for your velocity function, how you can solve for your position function, excuse me, if you're given an initial condition, like in this problem, x of 0 equals 0, to solve for your position function like we did right here. And this right here is our answer.